Okay, awesome. So we're going to kind of work through some examples today, and then hopefully have time for the page that you guys picked up. For those of you online, it's on the Moodle page in class number 4, so you can grab it there when we need it, if we need it. So this should be kind of the end of our notes from last class, right? So you should have this. What we're basically going for, and what we're going to dive into a little bit, is this broader framework, right, where we're saying that we can look at physical laws and map physical laws that we typically think about for like a defined system or a defined mass, and we can map them into this framework where we have like how that works for an individual mass. That's this term. So this is the system. So the rate of change for a system. So again, like the rate of change of momentum, or the rate of change of mass, or the rate of change of energy. First, so depending on which physical property, we can map that onto an accumulation. So this would be accumulation inside our control volume. And this is the flow out of the control volume. Okay. This table that we have up here that we kind of finished last time with will help us map all of these physical laws into this. There's like a bad reflection or something? Are we good? Okay, we can all see. Okay, so this table will help us map each of these individual laws down onto into this framework. We call this this is Reynolds I can't spell transport theorem. So you may hear me talk about Reynolds transport theorem. I don't particularly care if you remember the name, but it's this idea of mapping physical laws onto a flow system control volume type picture. So let's see how that works. So for example, the conservation of mass. So we already know what this should look like, but just to see how we use that table. So we would pick out, okay, what is the rate of change of mass for a system? That's this term right here, dm dt, so that equals 0. So we would plug in 0 equals d dt, the integral of our control volume. This term eta, which is the intensive quantity, the intensive property. So that would be, in the case of mass, 1. Mass divided by mass. So 1 rho d volume plus the integral over our control surface, again, of eta 1 rho v dot dA. So what we get when we map conservation of mass is just exactly the continuity equation that we had before. Yeah, Liz.
V, if like the control surface, is that velocity and then the other one's volume?
Yes, so the V vector is velocity. the V with a line through it is volume. Yeah, good question. Okay, so let's look. We've done a little bit now with this for conservation of mass. So let's look, and I'm going to run through some of this and then do an example with momentum. And then hopefully we'll have a chance for you to get working on this too. I think to get a handle on momentum and how it works, it's going to take quite a bit of practice. So we'll probably gloss over some things, but I want to get you guys like actually practicing using this before too long. So for momentum, right, for momentum, F equals MA, which equals dP dt, the change in momentum with time. So that's right. That's our fundamental law. We're going to map this law, right, using so that's going to be this section here, Newton's second law. So how does momentum change for a system? That's going to be right, the force equals d dt, the integral over our control volume, right? We're using this framework. So now eta, so that's velocity. Velocity, density, d volume, plus the integral over our control surface of velocity, density, velocity dotted with dA. Okay, just plugging in the different things from our equation up there. So this is telling us how conservation of momentum works for a control volume. This is what we would typically call the momentum equation. It's a little bit trickier to deal with than conservation of mass. So we're going to have to be a little bit careful. The forces, this is all forces acting on our control volume. And this is the one that can get a little bit funky to think about and to handle. So this is so if we have like a fluid flowing through something, our control volume is like the fluid itself. Well, let me write it even more explicitly. So our we'll put a little star so that I can write to be the fluid where velocity changes are occurring. So it can be sometimes a little tricky to pick out exactly what we want our control volume to be. We want it to be the fluid where we're actually seeing changes in velocity, where we're seeing an acceleration. And it's going to be like specifically the fluid itself, not the pipe or nozzle or something. It's going to be the fluid that's inside of that thing. So those are the sum of the forces that are acting on that fluid. Then this is the, right, this is the rate of change of momentum inside the control volume. So right, basically this is so momentum is mass times velocity. That's why we have velocity times density over the entire volume, mass times velocity. And this is this term is the flux of momentum out of the control volume. So the net flux out. And so momentum is a little different because it has, right, we have extra vectors inside of our equation. Force is a vector and velocity is a vector. So we're going to have to typically deal with those as vectors. But we can break it apart into its x component, its y component, and z component, and solve each of those things individually. So we can break down into x, y, and z components. That's typically easier to do than trying to handle things in 2 or 3 dimensional vector notation. It's also nice because a lot of systems, we really only are looking at 1 dimension. So often we care about just a single dimension. I'll write the x, and then analogous would be the y and the z. So the x component would be, right, the sum of all the forces acting on that in the x direction. And I'll write this so that we have plus s b x plus rx. So usually there are a couple different types of forces that we might care about. That equals d dt. The integral, now this is the u component, because that's the x component of the velocity, u rho d volume, plus the integral over our control surface of u rho v dot d a. Okay, so a couple important things to note. So this gets rid of, splitting it up gets rid of a lot of the vector notation stuff. And then if we have multiple dimensions, then we would split it and first do the x dimension. Then we could next do the y dimension. Then we could do z and kind of treat them all independently. The one thing to note is this term, the velocity dotted with the area, that has to stay in vector notation because it's related to like flow across the surface. So that has to stay as a dot product. Those have to stay as vectors. But the other components we can break down into like u, just the x component of the velocity. All right, so what are these different forces? So this is surface forces. Surface forces are forces acting on the surface of the control volume. This is typically pressure. Right, so force equals pressure times area. So pressure can create surface forces, pressure times area. These are body forces. So what are body forces? Well, body forces are going to be from gravity. Right, so force body equals mass times gravity. And then these are kind of the strange ones of the group. We typically will call them, in our book, we'll call them reaction forces. They are surface forces as the result of some object acting on the fluid. So we'll do an example here where the reaction force is because we have a cone-shaped nozzle. So that's pushing on the fluid and causing it's causing it to pinch down into a smaller area and increase velocity. It's causing a change in velocity and acceleration, but it's that nozzle shape is pushing on the fluid and giving us a reaction force. So those are, it's going to be tricky to figure out how to classify each of the forces, but those are kind of the broad groups that they fit in. Pressure, body forces, and reaction forces. So we don't always have to we don't always have to take all of these into account. There are going to be a lot of problems where the body forces especially are going to be basically zero, or they're going to be exactly zero in, say, the x direction, right? Gravity might not be happening in the x direction, so we can say there are no body forces. Or it can be like a small amount of, the control volume is relatively small. So we don't have to consider the body forces because the other types of forces are just so big, right? We have numbers of like 1,000, and the body forces are like 0.1. So we go, okay, we don't have to consider that. And it's not a key part of the forces in the system. All right, so we'll do one quick example with this. So asking the question, has anybody ever done one of these? I can't make it big. I don't know why. Okay, how does this thing work? Oh, now it's getting big. What? No? I don't know what happened. Stop it. It just died. What? You're wrecking my fun videos. Stop it, computer. Here we go. Can you work? There we go. I just want to watch that guy crash. It's the real reason. Has anybody ever done this before? It looks super tricky, but also kind of fun. So how does this thing work? Okay, so I mean, at one level, right, you're shooting water down. They actually usually get the thrust from, you can see the hose that's attached to his feet. This guy is not good. I imagine that's what I would look like. It looks like it's all the same dude. Doesn't it? I'm going to assume that it's the same person. It looks like kind of fun. So, right, how does this thing work? Well, you are taking water. I think they're run off that jet ski. So that's using the jet from the jet ski to power it. Gonna watch him one more time. I'm gonna have to figure out how to get back to. Okay, so back to here. So how does that work? You're using the jet pointed down to create a force that's pushing you up. So let's look at that a little bit in detail. So here's our example. So this is the water jetpack. So we're going to say, right, here's our guy. This is the point where he's not crashing, which is rarely, but okay, so here's his little jetpack. Something like that. It's a good drawing. There's water squirting out of there. So there's going to be a force that's pointed down. Right? If we draw a little free body diagram, there's gravity pulling you down, and there's a force pushing you up from those two jets. I think in the video there were 4, but we're going to assume that there are 2. Okay, so I don't know what's the force of gravity, something. I'm going to just make it up. So the force of gravity is going to be equal to, it's going to be more than just the person, because it's going to also be some of the extra water. So it's going to be a little bit different than this, but again, for the sake of what we're doing here, we can get close enough. Let's put the x direction in the direction that again, just kind of as a sign convention. So gravity is going to be operating in the negative x. So the force from gravity is minus, I don't know, we'll say 100 kilograms times 9.81 meters per second squared. So that's right, 981 newtons. Negative. Okay, and I chose that number because it's an easy number for me to do in my head. So we have this force going down, so our jets must be creating that type of force pushing up. So let's look a little bit more closely at that force and see they have to be balanced. So we'll look at our control volume. So look at the jet nozzle. So it's going to look something like this. Okay, where there is fluid coming in there and coming out at a higher velocity, right? Because it's cone shaped, and the mass flow rate in has to equal the mass flow rate out. So if our area went down, our velocity goes up. Some dimensions. This dimension is, we'll say it's 5 centimeters, about 2 inches. And then it goes down to about 1 inch, we'll say. Okay, I'm mostly just making up these numbers, but in the ballpark. So we have some velocity here at the exit. So what velocity at the exit is required to give us enough force to hold us up and not have us fall down? Okay, so the basic equation that we're going to be using, again, we'll put our axes on this. So we have this as our x-axis. Okay, so our basic equation is linear momentum the linear momentum equation, which is that the sum of all the forces in the x direction is equal to ddt of u rho d volume plus the integral over our control surface of u rho velocity dot dA. Okay, so that's our basic equation. That happens because we only care about the x direction. So in x, so there are going to be forces in the y direction, but we don't have to care about them. So we only care about forces in the x. And we're going to assume that we're not, we're just hovering there and not like this guy, we're crashing every second, but we'll assume that we're just hovering there. So we'll assume steady state, which in this case would mean hovering. It doesn't mean that the water is not flowing. It means that the flows are not changing in time. So like if you looked and took a snapshot, right, water's going in, water's going out, things are changing, but they're not changing in time. So it doesn't mean, it's kind of a weird distinction because normally we would talk about steady state as like there's no acceleration happening. But if you're a water particle and you're traveling through our nozzle, you're going to start out slow and you're going to speed up and get shot out fast. It's just that that's not changing. You're just hovering there. So you have water constantly flowing through. It is accelerating. That's what's giving you the forces, but it's not changing with time. You're hovering. Does that distinction make sense? So that crosses out this. Okay, and that's going to be something that we do every single time. So our steady state equation is the sum of all the forces in the x direction equals the integral over a control surface of u rho v dot dA. Let's make another simplification. That we're going to use a lot. Let's simplify by assuming that velocity is uniform. Right, so that it's not a, right, so velocity, it looks like this, not that. So it's uniform over the entire area. And what does that do? It takes integrals out of the picture. It's not exactly true. So this is, it's not a true thing. But it's not super terrible either. So it ends up, it's a simplification. It makes our lives easier. We'll learn how to deal without it, without making that, but it certainly makes our lives and some of the initial analysis easier. So it's not true, but it's not exactly totally wrong. It's so the velocity changes where you are, whether you're at the wall, right? Then you have zero velocity. If you're in the center, that's where your maximum is. We're going to assume it's the same everywhere, but that makes this changes our integral to a sum. So we no longer have to integrate. So then our equation is the sum over the control surfaces of u rho v dot a. Okay, and this becomes a relatively easy thing to solve. So let's look at our system. We have, right, a nozzle like this. We have, we'll call this surface 1 and this surface 2. And by surface, right, that's like that surface and that surface. We only care about the surfaces for this that are where stuff is actually passing through. So here we have a velocity u1. Here we have a velocity u2. So the sum of all the forces in the x direction, that equals u1 rho v1 dot a1 plus u2 rho v2 dot a2. And now we have to look at our signs to make sure we get the sign conventions all correct. So that's where the dot product comes in handy. Right? These A terms, these are outward normals. So Fx equals u1 rho. So what does our dot product mean? So our velocity is coming into the surface, our area is pointing out of the surface. Those are opposite, so that's going to give us a negative dot product. This will be negative u1 a1 plus u2 rho. Now our area and our velocity are both pointing down. They're both pointing out, so that's going to be a positive dot product. So this will be positive u2 a2. Okay, so our net force, again, we can look at this. We know we also know that and this is a common thing that we'll do in almost every, we also know that conservation of mass must be obeyed. And these two equations are going to go together like hand in hand in problems. So we have to obey F equals ma. We also have to obey conservation of mass. Conservation of mass is what's going to relate our inlet flow rate to our outlet flow rate. So conservation of mass would be right, 0 equals the inner dt of rho dv plus the integral over our control surfaces of rho v dot dA. So we're going to simplify this in the same way that we just simplified the linear momentum equation. So we know, so our same assumptions or simplifications. So this would be steady state and uniform velocity. That would give us 0 equals the sum of rho v dot A, which is equal to rho negative U1 A1 plus rho U2 A2, or rho U1 A1 equals rho U2 A2. The mass flow rate in equals the mass flow rate out. Okay, if this is true, we can relate then the inlet velocity to the outlet velocity. So our outlet velocity, U2, is going to be equal to U1 times the ratio of the two areas. Okay. So this is, that's conservation of mass. Now we can plug that into our equation for our linear momentum equation. So the net force in the x direction is equal to density is U2 squared A2. Right, I'm just plugging it in and kind of simplifying that equation. So we're bringing that equation down here. Plus, and now anywhere where I saw U1, I'm going to replace it with so this is plus, or sorry, minus density U2, am I getting this wrong? U2 A2 over A1 squared times A1. Okay. I think that's correct. Okay, so now we want to plug in and find what our final velocity is. So we would want to say, right, 450 newtons. Right, this is 1/2 force of gravity. So that's what our net force in the x direction has to be to keep us up, 450 newtons. So that has to equal now values for these things. So density is 1,000 kilograms per meter cubed. Our velocity, we don't know. That's what we want to find. So that's our exit velocity, U2 squared. We'll leave this as a variable right now, A2, minus 1,000 kilograms U2 squared. This is A2 squared over A1 A2 equals pi R2 squared. A1 equals pi R1 squared, which was 2.5 centimeters and 5 centimeters. So this is, let's see, this is 4.9 centimeters squared, or 4.9 times 10 to the minus 4 meters squared. And that's 19.6 centimeters squared. 19.6. Then it's simply just like plugging things in and solving for u. So we can solve for u2, that would be 35 meters per second, or something like 75 miles per hour. Something about like that. So I skipped over a couple steps because I wanted to give you at least 5 or 6 minutes so that I can talk to you about the problem that we're doing on this worksheet. So it looks like we have 7 minutes left. That's enough time to at least get started. The big things, we're always going to be using conservation of mass. Almost always going to be using conservation of mass in tandem with the linear momentum equation. But the real big thing is usually, so if we make this assumption where we have uniform velocity, that gives us that as a starting place. So uniform velocity is a handy assumption because it gets us from the land of integration to the land of sums and normal multiplication. Then it becomes, how do you track all of the forces happening in your system, pressure and gravity and things like that. So we're going to have, there will be a couple examples. I'll go through like full examples in detail and make videos of them on Moodle so you can watch them, because I think it's something you'll need to get practice with it. But let's spend at least 5 minutes trying to think about the problem that you have in front of you. It may take more than 5 minutes. I don't know if that's enough time, but we'll at least start thinking about it. Right, so the key to this problem is picking a good control volume. Right, and you want to choose a control volume where the acceleration is happening. So you should be like kind of encompass the full range of the acceleration. So your control volume, you want it to be from where it is going at its like normal velocity to where it stops completely. So it's going to be the area over which that velocity is changing. So there are going to be two forces on this table. One is going to be the weight of the corn. The other is going to be the force that's required to stop the corn from falling. Okay, so the corn's coming in and it's coming from going at 2 meters per second and coming to a complete stop. There has to be a force involved in order to make that velocity change happen. Okay, so corn's coming in, you're stopping it, that creates a force. And then there's a second force that's like the weight of the corn. So you really need to care about like what is the force required to stop the corn. And if that's 50 newtons, then like your scale's going to read 50 newtons.
Yeah.
So this is a good, this guy. So kind of the trick is that it doesn't, like the velocity at the outlet of the control volume is going to be 0 in the x direction, or in the up and down direction, because the corn is going to come out like the sides, right? Because there's a flat surface there. Right, so to draw. So you have corn coming down and then going this way and that way. So in this dimension, if we call that x, if this is our control volume, right, it comes in at some velocity, but it doesn't go out in the x direction at any velocity. It goes out in y and z, but not x. But we only care about the momentum in x. So this would be side 1. Bottom would be side 2. Okay, it is 12:50. I'm going to post a video of a very similar problem, but this is going to be due Friday. I guess I've done other videos of very similar problems, so if you're going through and thinking about this, but I want you to think about this before you jump into some complicated stuff. It'll be a little bit of a chance. Yeah, so bring it, you can bring it to class. Look forward, like, at the, probably 3 o'clock this afternoon, you'll get the deal out of the book. Yeah. Probably for the month. Well, no, I. Big Caroline? What? What's the time that you once you're in? For your own. Shoot. Usually my
Well, where's the public? Alright, guys, I thought I'd come back so long. How are you? I'll